Imagine for a moment the solid ground beneath you suddenly giving way. It's a bit unsettling, right? A reminder of these huge forces locked deep inside our planet. Today we're going on a journey really to understand just that. How energy born miles underground travels up and, well, shakes the buildings we live and work in.
Yeah, we'll be looking at the basics of earthquake theory, tracing that path of energy as it ripples through the earth. It's this invisible force, but it shapes our world in really significant ways.
Exactly. And our mission today is to break down that whole process. Where does the energy start? How does it move? And crucially, what factors decide how much shaking we actually feel up here? So maybe to kick things off, what actually is an earthquake, fundamentally?
Well, in simple terms, an earthquake is a sudden release of energy. Stress builds up along a fault, that's a fracture in the Earth's crust, and then it lets go. It's all driven by the movement of tectonic plates.
Tectonic plates, so these giant slabs of rock are constantly moving. That sounds like it would definitely build up tension. Where does this energy actually gather and why?
That's right. The Earth's surface isn't smooth. It's broken into these tectonic plates. And where they meet, at the boundaries, they interact. They push, they pull, they grind past each other. Often they get stuck due to friction. But the plates keep trying to move, so the rocks near the boundary start to deform, kind of like stretching a rubber band. They store energy elastically.
Ah, so it's like winding something up tighter and tighter.
Precisely. And the stress builds up over potentially very long periods. Then eventually that stress becomes too much for the rocks to handle.
The knobs map.
Exactly. The rock breaks or an existing fault slips suddenly. That rapid movement releases all that stored elastic energy, and that's the earthquake.
Okay. Now, when that rupture happens, I know there are two key points people talk about. The hypocenter and the epicenter. Can you clarify those for us?
Sure. The hypocenter, sometimes called the focus, is the actual point underground where the rupture begins. That's the origin. The epicenter is the point on the Earth's surface directly above the hypocenter.
Got it. So the energy starts deep down at the hypocenter and radiates out from there.
Correct. It travels outward in all directions from that starting point.
So how does that released energy actually travel? How does it get from the hypocenter to shake the ground, say, miles away?
It travels as seismic waves.
Yeah.
These are basically waves carrying mechanical energy through the Earth. We usually talk about a few main types. First, you have P waves for primary waves. They're the fastest. Think of them as compression waves, like pushing and pulling a spring or a slinky. They travel by compressing and expanding the rock.
Okay, the speedsters. And they can travel through anything?
Pretty much. Solids, liquids, gases, they're the first ones to arrive at a seismograph station.
All right, what comes next?
After the P waves come the S waves, or secondary waves. They're slower. These ones are shear waves. Imagine shaking a rope up and down. The wave moves along the rope, but the rope itself moves side to side, perpendicular to the wave's direction.
So a different kind of motion.
A different motion, yes. And a key thing about S waves is they cannot travel through liquids, only solids.
Ah. So if an S wave hits, say, the Earth's liquid outer core, it just stops.
It stops or gets converted, and that inability to pass through liquids is actually one of the main ways scientists figured out that the Earth has a liquid outer core. It gives us clues about the planet's internal structure.
Fascinating. Okay, P waves, S waves.
Yeah.
Are there others?
Yes. Then we have the surface waves. As the name suggests, these travel along the Earth's surface or just below it. They're the slowest of the main types.
Slowest, but I have a feeling they're important.
Very important. They're often the most destructive. Think of ripples on a pond surface. Waves have larger amplitudes, meaning bigger ground movements, and they can last longer. They cause that rolling or swaying motion that does so much damage to buildings.
Right. Those are the ones that really interact with structures on the surface.
Exactly. They spread out and shake the ground and anything built on it.
Okay, so we mentioned faults earlier, the fractures where the rupture happens. You said there are different kinds based on the stress?
That's right. Faults are these zones of weakness. We generally classify them based on how the blocks of rock on either side move relative to each other, which is dictated by the type of stress. First, you have normal faults. These happen where the Earth's crust is being stretched or pulled apart, tensional stress. One block, the hanging wall, drops down relative to the other block, the footwall. You see these a lot at mid-ocean ridges, for example.
Okay, pulling apart causes one side to drop. What about pushing together?
That causes reverse faults, sometimes called thrust faults. This is from compressional stress plates pushing into each other. Here, the hanging wall gets pushed up relative to the footwall. Subduction zones, where one plate dives under another, are prime locations for these.
Makes sense. Compression pushes things up. Is there a third type?
Yes, strike-slip faults. Here, the stress is shear stress. Imagine two blocks sliding horizontally past each other, side by side. The movement is mostly lateral.
Like the San Andreas fault.
Exactly like the San Andreas fault. That's a classic example of a strike-slip fault system.
So the type of fault really tells you about the bigger picture, the plate tectonics happening in that region.
Precisely. Plate boundaries are where the action is. Convergent boundaries, where plates collide, give you reverse faults, maybe mountain building, big earthquakes. Divergent boundaries, where they pull apart, you get normal faults, like in rift valleys or mid-ocean ridges. And transform boundaries, where they slide past each other, that's where you find strike-slip faults. These interactions are what load the faults with stress in the first place.
And when that stress is released at the hypocenter, that's the earthquake's energy release. How do we actually measure how much energy is let loose?
That's where we talk about magnitude. The scale used most often now is the moment magnitude scale, or MERW. It's generally considered the most accurate measure of the total energy released by the earthquake at its source.
Right. MERBO. And I've heard it's logarithmic. What does that mean in practical terms?
It means each whole number step up on the scale represents a huge increase in energy. It's roughly a 32-fold increase in released energy for every 1 unit increase in magnitude.
Wow, 32 times. So a magnitude 7 isn't just a bit bigger than a 6, it's, well, vastly more powerful.
Immensely more powerful. To give you a rough idea, a magnitude 3 might feel like a nearby small explosion. A magnitude 5 could be like a large conventional bomb, enough to cause some damage. But a magnitude 7 releases energy on the scale of a major nuclear weapon, potentially devastating a city. And an 8 or 9 is releasing energy on a truly colossal scale.
That really puts it in perspective. What about the older Richter scale? We still hear that sometimes.
Yeah, the Richter scale was developed earlier. It's based on the amplitude, the height of the largest seismic wave recorded on a specific type of seismograph. It's also logarithmic, but it tends to be less accurate for very large earthquakes compared to the moment magnitude scale. MERW is better at capturing the true size of those massive events.
Okay, so magnitude tells us the energy at the source. But the shaking we actually feel at a specific spot on the surface can be different, right, depending on where you are.
Absolutely. That's where intensity comes in. We measure intensity using scales like the Modified Mercalli Intensity Scale, or MMI. Unlike magnitude, which is one number for the whole earthquake, intensity describes the severity of shaking at a specific location. It's based on observed effects, what people felt, how objects moved, damage to buildings.
So it's more about the impact in a particular place.
Exactly.
Yeah.
And it depends heavily on your distance from the epicenter, yes, but also crucially on the local geology, the type of soil or rock beneath you, and even the type of building you're in.
So you could be further away from a big earthquake, but be on soft soil and feel stronger shaking, maybe get more damage, than someone closer but on solid rock.
Precisely that. Soft soils can amplify shaking significantly. The MMI scale reflects this variability. It goes from Roman numeral I, not felt, up to X or higher, representing catastrophic destruction.
Like what would an MMI of IV feel like versus, say, 8?
An MMIV might be light shaking, felt indoors by many, maybe rattling dishes. An MMI8 would be severe shaking, considerable damage to ordinary buildings, even some collapse. Chimneys might fall. It's a big difference in impact.
Okay, so the energy radiates out, but it must lose some steam along the way, right? It doesn't just travel forever at full strength.
No, definitely not. The waves lose energy as they travel. We call this damping or attenuation. There are a few reasons for this. One is material damping. Different materials absorb energy differently. Hard, solid rock like granite lets waves pass through relatively easily with less energy loss, low damping.
Okay.
But softer materials like sand, clay, or sediments absorb more energy. They have higher damping, so the waves weaken more quickly as they pass through these layers.
So the ground itself can sort of muffle the shaking.
It can. Another factor is geometric damping or geometric spreading. As the waves radiate out from the hypocenter, the energy spreads out over a larger and larger volume, like ripples on a pond getting wider.
So the energy density decreases with distance.
Exactly. The wave amplitude naturally decreases as it travels further, even if the material isn't absorbing much energy. And then there's frequency damping, too.
How does frequency play into it?
Generally, higher frequency waves, the shorter, choppier ones, like S waves and some surface waves, tend to get damped or lose energy more quickly than lower frequency waves, like P waves.
So the longer, slower waves can travel further without losing as much punch.
That's often the case, yes, which has implications for what kind of shaking you might feel far from the epicenter.
You mentioned soil conditions amplifying shaking. Can we dig into that a bit more? How do the ground layers right beneath us and the buildings on top interact with these waves?
This is super important for understanding damage patterns. Those soft soil layers, like river sediments or landfill, don't just damp waves, they can actually amplify certain frequencies. The waves slow down when they enter the soft material, their amplitude increases to conserve energy, leading to stronger shaking at the surface.
Amplification. Okay, that sounds bad enough.
It gets worse. There's also resonance, everything like the ground layers. A building has a natural frequency or period at which it prefers to vibrate. Like pushing a swing at just the right rhythm makes it go higher.
Right.
If the frequency of the incoming seismic waves matches the natural frequency of the soil layer or the natural frequency of a building sitting on that soil, you get resonance. The vibrations build up, become much larger, and dramatically increase the risk of damage or collapse.
Wow. So you could have the ground amplifying the waves and the building shaking itself apart because the wave frequency hits its resonant sweet spot.
That's the dangerous combination, yes. It highlights why knowing the local soil properties and designing buildings with appropriate stiffness and damping is so critical in earthquake zones.
Absolutely. So thinking about designing those buildings, what key earthquake parameters do engineers really focus on?
Well, several are crucial. A big one is peak ground acceleration, or PGA. That's the maximum acceleration the ground experiences during the shaking. It's a measure of how hard the ground is pushed back and forth.
And why is acceleration so important?
It's because acceleration times mass equals force. PGA gives engineers a direct handle on the inertial forces the earthquake will impose on a structure. It's especially key for stiffer, shorter buildings, which are sensitive to rapid shaking.
Okay, PGA. What else?
Earthquake duration is also vital. How long does the strong shaking last? Longer shaking means the building is stressed for a longer time. This can lead to fatigue in materials or allow damage to accumulate. Far-field earthquakes often have longer durations.
Right, it's not just how hard it shakes, but for how long.
Exactly. And then there's the frequency content of the ground motion. We've touched on this. Is the shaking dominated by high frequencies or low frequencies?
Because that affects different types of buildings differently.
Precisely. High-frequency shaking, common near the fault, tends to be more damaging to short, stiff structures. Low-frequency shaking, which travels farther, is more likely to excite taller, more flexible buildings, think skyscrapers, potentially leading to resonance problems for them.
So engineers need to consider the whole signature of the expected shaking, its peak intensity, duration, and frequency mix.
Absolutely. It's a complex picture.
This brings up the difference between near-field and far-field earthquakes. What are the main distinctions in their effects?
Good question. Near field refers to locations very close to the fault that ruptured, maybe within 10 or 20 kilometers. The shaking there can be quite different. You often get very strong impulsive motions, sometimes called flings, which can include significant vertical shaking and even permanent ground displacement, where the ground actually shifts and stays shifted. The shaking can start very abruptly.
Intense and sudden. High frequencies probably dominate.
Often, yes. High frequencies, sharp pulses, it's very demanding on structures. Far-field earthquakes are those originating further away, say more than 20 kilometers or so. By the time the waves reach a far-field site, the high frequencies have often been damped out more. The shaking tends to be dominated by lower frequencies, longer periods, and it typically lasts longer.
So near field is like a sudden jolt, maybe a fling,
Yeah.
while far field is more of a prolonged rolling or swaying motion.
That's a pretty good way to think about it, yeah. And the design implications are different. Near-field design needs to account for those strong pulses and potential ground shifts, requiring really robust connections and maybe special damping systems. Far-field design might be more focused on how tall, flexible structures respond to the long period, long-duration shaking, worrying about resonance, and overall building sway.
It's really quite amazing when you trace it all the way through from a slip deep underground, the different waves traveling, losing energy, being amplified by soil, and then finally how different buildings respond based on distance and frequency.
It really is. It's a complex chain of events. Understanding that whole journey, the energy release, the wave propagation, the damping, the crucial role of local site conditions, and how structures interact with the shaking that's fundamental to figuring out earthquake risk and how to build more resiliently.
It truly underscores the power and complexity of these natural events. So as we wrap up this deep dive, maybe something for you, our listeners, to think about. Knowing how much the frequency content of seismic waves matters, how high frequency versus low frequency shaking affects different buildings. How could engineers better use that knowledge?
How could understanding the likely frequency characteristics in a specific region help them tailor building designs even more effectively to resist the kind of shaking they're most likely to face? It's a fascinating question at the intersection of earth science and engineering, with really significant implications for safety in earthquake-prone areas worldwide.